All right, let's get started. We're gonna be uploading the handout to the website in just a few minutes, but we're gonna get started with the class. So at any point, if you are confused or you need uh, help, you can obviously ask in the chat or to one of the instructors. Yeah, make sure you're just asking one of us. But you can also refer to the handout for today's class, which is gonna be uploaded on the website in just a few minutes. The link to the website uh, will be in the chat. Can Alan or one of you put the link to the classes and handouts page in the chat? And yeah, with that, let's just get started. So again, if you have questions, feel free to ask, and the handout will be uploaded to the site soon. So with that, Suyash and Nivid.
All right, so let me share my screen. We're in the chat here. Okay, yeah. All right, today we are going to be continuing our discussion on sequences. So yeah, last week I think we covered just certain types of, I think, just arithmetic sequences. And I think the sum of an arithmetic sequence, if I recall, I think we may have briefly touched on geometric sequences. Today we'll be covering some further topics. So it'll be Nivid and I teaching today. And like Ron said, you can ask, all four of us are here, so you can ask any of us in the chat if you have a question. All right, so let's see. I guess, did you want to? We're going to do this part.
Right. So we briefly went over this last time, but the first thing we're going to be talking about today is summing arithmetic sequences. So if you remember from last time that our arithmetic sequence is a sequence that increases by a fixed number at each step. So the general formula for an arithmetic sequence, or the general form for an arithmetic sequence, is a plus d, a plus 2d, so on, all the way to a plus n minus 1d. And a is the original term, d is the common difference, and n is the number of terms. So last time we briefly went over how to get the sum of the sequence, but the following theorem that we're going to show shows how to get the sum of an arithmetic sequence of finite length. And finite length just means that we know how many terms there are. There's 5 terms, there's 10 terms, it doesn't matter, but we know how many terms there are. So the theorem is that the summation of the terms of an arithmetic sequence with n terms is the first term a first, the last term with the first term a first and the last term a last is n times a first plus a last divided by 2. So an easy way to remember this formula in like a more wordy way rather than a formula way is the number of terms times the average of the first and last terms. So this is really simple and it's really useful in a wide range of topics and problems, and a lot of problems that aren't at all related to arithmetic sequences will kind of boil down to this formula and boil down to an arithmetic sequence. So this theorem allows us to compute the sum of an arithmetic sequence if we know the first term, the common difference, and since the last term of an arithmetic sequence is the first term plus the number of terms minus 1 times the common difference, we can use this bottom formula to find out what the last term is, and then we can, using all those pieces of information, find out what the sum of the arithmetic sequence is. So just to kind of go over the slide again, how to find the sum of an arithmetic sequence is the number of terms times the average of the first and last term. That's like the main takeaway here. All right, so Yash.
Okay, so we're going to do a quick example with arithmetic sequences. So there we go. All right, so an arithmetic sequence has first term A and common difference B. If the sum of the first 10 terms is half the sum of the next 10 terms, what is the ratio A to D? Sorry for the typo there. Take a few minutes. Think about this.
again, if you have any questions or you want to confirm your answer, then you can send it to one of us, one of the instructors.
I think what Nivet just talked about with finding the sum of an arithmetic sequence, that's very important here. Give it another minute. I'll give it at least another minute or two on this one. Some people appear to be needing a little
I
more
only
time.
got responses in the chat for me, so I think maybe people are still working on it. All right, I've gotten quite a few responses, so you actually want to go through the walkthrough.
All right, so I'll go through this slowly, but okay. I know there's some people who are still trying to figure this one out. So let's look at some of the first 10 numbers. The first term is A, and the 10th term is A plus 9D. Remember, because it's A plus 0D, A plus 1D, all the way to A plus 9D. So using the formula that Nivet just described, remember, it's the average of the first and last terms times the number of terms. We know the number of terms is 10. We know there are 10 terms there. And the average of the first and last terms, well, the sum of those is 2A plus 9D. So the average is A plus 4.5D. When you multiply that by 10, you just get 10A plus 45D.
Can you keep that up, like the formula, because I just joined?
Okay, we're working on this right now. I'll drop that in the chat, though, somehow.
Sure, I'll put the formula in the chat.
Yeah, okay, well, we'll go ahead and do that. Okay. So the 11th term is A plus 10D, and the 20th term is A plus 19D. So we can do a similar thing for that. Average of first and last times number of terms. There are, again, 10 terms. So the sum is 2A plus 29D. Divide that by 2, it's A plus 14.5D, but then you have to multiply that by 10 for 10 terms. That's 10A plus 145D, yeah. Now, okay, so, okay, we see that relationship there. And we know that the sum of the second set of 10 terms is twice the sum of the first 10 terms. So we can apply that together. So we get that relationship. Does everyone understand how we got here? And it looks like we cancel out the 5s because we don't really need those. Those are on both sides, those cancel. Does anyone have any questions about how we got here? So to recap, we just applied the formula for the first 10 terms, the next 10 terms, and then we know a relationship between them. So that's how we got here. Now, it's one equation and 2 unknowns, so we can't actually solve for A and D, but we don't need to know that. We only need to know that ratio A over D. Now, okay, so this goes, all right, let's see what. All right, I'll go over this again. But at this point, once we have this equation, it's pretty easy. You could just expand it. You move A to one side and D to one side. You end up with 2A equals 11D. Since we're wanting to find A over D, you just divide both sides by 2D, and you get A over D equals 11 over 2. So let's actually go back and go walk through this again. So the sum of the first 10 terms is half the sum of the next 10 terms. So the formula that we use is average of the first and last terms multiplied by the number of terms. So we know the first term, we know the last term. So we just take the average and multiply it by the number of terms. Now, since we have an even number of terms, we can just do the sum of them multiplied by half the number of terms. That's equal mathematically the same thing. So, and then similar thing from 11 to 20, because that's the next 10 terms. Again, sum of the first and last terms multiplied by half the number of terms. So this is what we get for that and for that. Okay, so then what we have is the sum of the first 10 terms is 5 times the quantity 2A plus 9D. And the sum of the next 10 terms after that is 5 times, okay, this should be parenthesized, 2A plus 29D. Sorry. Typo there, that's all right. And now we know the relationship. This is 2 times this. Now, when we want to equate them. Now, at that point, we can cancel the 5s out because those appear on both sides. So you're left with 2 times this is equal to this. Again, that should be in parentheses. We made a little mistake there. And then from there, it's pretty straightforward. Okay, any other questions? Please drop it in the chat. I know that was tricky, but. Okay, you could assume A equals 1. You don't have to, but that's one thing you could try if you're having some trouble here. But all right. Niven, you can take it from here.
All right, so the next thing we're going to look at is geometric series. So we're going to move a little bit from arithmetic sequences to geometric sequences. And before we start all this stuff, there's one key note that we had to say about terminology. There's a key distinction between series and sequences. So far, we've been talking about sequences. Sequences, a series is usually defined as a sum of sequences. So let's say the example we just had, the sequence could be like 1, 2, 3, 4, 5, 6, so on. Or it could be a geometric sequence, which is like 2, 4, 8, 16, so on. But then when we say series, it means that it's the sum of the sequence. So if our sequence is 1, 2, 3, then the series is 6, because 1 plus 2 plus 3 equals 6. So a sequence, like I said, is just a list of numbers. And also note that sequences can also be infinite. So far, we've been dealing with sequences that are finite. So like we know how many terms there are, but sequences can also be infinite. There could be an infinite number of terms in the sequence. So a geometric sequence is a sequence which is multiplied by a fixed quantity between each term. So we generally write them as AR, AR squared, AR cubed, where A is the initial term and the common ratio is R. So this is kind of review from last time, but this is a sequence. So now we have to ask a question. Is it possible to find the sum of the values of an infinite geometric sequence? If we have a finite geometric sequence, like 2, 4, 8, we can just add the numbers together, 2 plus 4 plus 8, and we get 14. But is it possible to find the sum of the values of an infinite geometric sequence? Well, we're trying to find A plus AR squared plus AR cubed all the way up until kind of infinity, however big or small the last term is. So if R is greater than 1, or the common difference is greater than 1, then it means that the infinite sum is undefined, or it diverges. So in the example I just gave, 2, 4, 8, if this sequence went on and on and on, then we would never be able to find the sum of this because the terms would keep getting bigger and bigger and bigger. So this is what we call an undefined sum, or we call it a divergent sequence. But if R is, so for example, if R is equal to 2, which is greater than 1, and A is equal to 1, in this example here, then this will just, the sum will keep getting bigger and bigger and bigger, and we cannot say what the total sum is. So this example does not converge onto a fixed number since the terms are each bigger than the last. All right, so in the previous slide, we claimed that if R is between 0 and 1, then a geometric sequence with a common ratio R converges. So this means that if the common ratio between terms is between 0 and 1, then we can find what the total sum of the sequence is. So let's see an example of this when R is equal to 1/2 and the initial term is 1/2. So we want to convince ourselves that 1/2 plus 1/2 squared plus 1/2 cubed, which is equal to 1/2 plus 1/4 plus 1/8, and this sequence goes on infinitely, converges to a finite value. We want to kind of see that, can we add all these things together and can it come to a finite number? Can we say that all of this is equal to some number that we don't yet know? So we will prove this very soon, but here's a picture which kind of explains this. So we start off with 1/2, and then if we add 1/4, well, we have 1/4 left on the number line. Now if we add 1/8, we have 1/8 left on the number line. And if we keep going and keep going, we can see that we'll eventually keep adding, getting closer and closer to 1. And if the series goes on infinitely, then the sum of all the terms in the series would be 1. So we can actually prove that the sum of these terms indeed converges to 1, and we will be doing this soon. All right, so yeah, you want to take over from here?
So, okay, let me. So yeah, we're now going to show that this indeed equals 1 because I guess intuitively this doesn't make sense because you're actually getting halfway closer to 1 each time as demonstrated. 1/2, 1/4, and then 1/8 would get you halfway, halfway, halfway. So that kind of seems intuitive. We're not going to prove it because we want to prove that it's converging to 1 and not 0.999. So let's see that here right now. So, and while this now, that is important. While this is the sum of an infinite sequence, the sum of the infinite sequence is finite because you can see the terms are getting smaller and smaller. Now, here's the thing. So if the terms are getting larger, obviously it's not going to converge to a finite value. Yeah, we shouldn't have this 1 here, guys. We're only looking at, okay, I don't know which problem it actually is, but you'll see it. If you add that 1 at the beginning, then it actually becomes 2 because you start at 1. Go 1/2, 1/2 squared. So because the terms are getting smaller, there's a chance that it might actually converge to a finite value. But even if the terms are getting smaller, it's still possible that it might go out to infinity. So as some terminology, if a series sums to a finite value, we say that that sequence converges. I don't know if we have that down here, but if it goes to infinity, we say it diverges. Now it turns out for a geometric series, if that R ratio is between -1 and 1, it will always converge. In this case, it's 1/2. So yes, that falls under this category. So define S. Okay, I don't know. So like I said, this one would be equal to 2. So let's define S. Now, we're going to multiply everything by 2. So on the left, we have 2s. 1 doubles to 2, 1/2 doubles to 1, 1/2 squared doubles to 1/2, 1/2 cubed doubles to 1/2 squared, and so on. Does everyone understand that? We're just doubling the sequence. So in general, 1/2 to the power of n becomes 1/2 to the power of n minus 1 because 2 and 1/2 are inverses. So it just cancels one of the 1/2 out. All right, so now you kind of might see where this is going because the only difference between S and 2s is that the 2s has an extra 2. Everything else is the same. Remember, this goes on forever. 1 in both, 1/2 in both, 1/2 squared in both. All these terms will appear in both. So the key is to subtract the 2 equations, and most of the terms will vanish. 2s minus s. So 2s is 2 plus 1 plus 1/2 plus 1/2 squared plus 1/2 cubed. That's what we have here. Someone put their hand up. Okay. S is just 1 plus 1/2 plus 1/2 squared. Everything except the 2 cancels out. Does everyone see that? Yes? 1 cancels out. 1/2 cancels out. 1/2 squared cancels out. All you're left with is 2. 2s minus s equals 2, so s equals 2. So that was kind of pretty interesting because it suddenly just all came together. Because from this, it doesn't look like you can really figure it out. But using the two equations, they're very similar. So you just subtract them and voila, we got it. And yeah, so we could also just take away that 1, and that will just subtract 1 from both sides. 1/2 plus 1/4 plus 1/8, and so on equals 1. Yeah, something like that. Yeah, infinite series, that's a new concept for most people. Even just saying it's like, how can an infinite series add up to a finite value? That might be kind of counterintuitive. So if there are any questions about how this works, please ask. Otherwise, we're just going to move on here. Yep. Let's go with this proof.
All right. So now that was like a really specific example, but now we're going to generalize them into general geometric series formulas. And so we can do we can generalize this method series. So the common ratio satisfies that the absolute value.
David, I think you're cutting out. Is he cutting out for you guys as well, or?
Yes, he is.
Yes.
All right, I think I'll take this. Hopefully Nivid's situation improves. And okay, so yeah, Nivid's just frozen for me. I don't know about you guys, but all right. I wanna just yeah. So yeah, Nivid, hopefully he'll come back and you can keep going from here. All right, so we want to know we want to generalize this method. So we looked at one particular series. Let's see, yeah. So we looked at 1 plus 1/2 plus 1/2 squared. We want to look at any series now with any starting value and any common ratio. So we're just going to give you the formula right now. So A is your starting term, and R is your common ratio. Then you start with AR squared, AR cubed, AR to the 4th. The sum of all that just comes out to A over 1 minus R. It's a surprisingly nice formula. Now the absolute value of this ratio has to be less than 1. It won't work otherwise. And that should be pretty obvious because if R is greater than 1, then these terms just grow forever. It's obvious it's not going to converge to a finite value. But it turns out if the absolute value is less than 1, then it will always converge. So let's see this. So this will be, okay. Now, we start with S equals A plus AR squared plus AR cubed. Okay, that's the sequence we have. Now, we want to multiply both sides by R. Well, actually not R, well. So in the example, we multiplied both sides by 2, but we could have also multiplied both sides by 1/2. And that's what we're going to do here, multiply both sides by R. So we took a slightly different approach in the previous problem, but this works better for the general case. So we're multiplying both sides by R. So here we have S times R. Here, A becomes AR becomes AR squared becomes AR cubed becomes AR to the 4th. Now, just like the previous example, most of these terms are common. So you can subtract SR from S, and that will cancel everything except A, because AR appears in both, AR squared appears in both, AR cubed appears in both. So you're left with S minus SR equals A. S equals A over 1 minus R. All right, so that is the general formula. Now you must check that R, absolute value of R is less than 1. So obviously if R equals 1, this just becomes undefined. If R is greater than 1, then obviously you get something kind of bizarre. So if you, for example, when A equals 1 and R equals 2, you get negative 1. That doesn't mean that 1 plus 2 squared plus 2 cubed equals negative 1. No. You must check that the absolute value of R is less than negative 1. Now, it's also worth noting that this does work for negative values of R that are greater than negative 1. In that case, it becomes an alternating series because you could say, let's say you did 2 and your common ratio was negative 1/2. That would be 2 minus 1 plus 1/2 minus 1/4 plus an 8 minus 1/16. and that would also convert to something finite, but it would be like jumping around. So it would be like da 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 da. It would also approach a finite value there. So are there any questions about this? So I'll actually go over this again. So to clarify, what we did here was we started with this sequence here that s equals a plus ar plus ar squared plus ar cubed and so on. We multiplied by r on both sides, and that enabled us to subtract sr from s because that cancels out everything except for a itself. And now we divide by 1 minus r. Now we kind of hit a step here. So you factor on s, this is equal to s times 1 minus r, and then s equals a over 1 minus r. David, are you here? Can you hear me? Or is your internet better? Okay.
I think he was forced to leave the meeting. I can try to contact you, but for now, why don't you just go ahead for now? So
All right, then I guess I'll just continue. Yeah, that's totally fine. So let's do an example kind of illustrating how this works. All right, many of you already know this, but take just a moment to think about this. Because we're going to present a geometric proof, a proof using geometric series for this fact. I'm sure this is something many of you have heard of before, but yeah, so I'm not going to stop for too long on this, but this is equal to 1, right? Now there are a couple of different ways to prove this. Okay, someone's asking what do A and R represent? So A represents the first term of the sequence. R represents the common ratio between the terms that defines the geometric sequence. All right, hopefully that clears things up. So for example, I'll actually go back here. In this example, the first term was 1. The common ratio was 1/2 because we are multiplying by 1/2 each time. Going back here. So you've probably seen many proofs of this. First of all, if 0.9999 forever was not equal to 1, there would be something in between them, but you just can't find something in between them. The other thing you could do is like you say, oh, well, 1/3 equals 0.333333, and if you multiply both sides by 3, you get 1 equals 0.999999. Let's take a look at a geometric series proof for this. So this is, you can think of it as 0.9 plus 0.09 plus 0.009 plus 0.0000009. That's equal to 9/10 plus 9 over 100 plus 9 over 1000 and so on. That is a geometric series. This is a geometric series. The first term is 9/10. The common ratio is 1/10. You see why? Because you're multiplying by 1/10 each time. So it would be 9/10 over 1 minus 1/10. That's equal to 9/10 over 9/10. That's equal to 1. Just what we expected. That's another proof to illustrate this. All right, David, it looks like you're back, so I'll let you take this.
All right, so now we're going to work through a contest, an AMC example. So let a plus r1, a plus a ar1 plus ar1 squared plus ar1 cubed, and a plus ar2 plus ar2 squared plus ar2 cubed be two different infinite geometric series of positive numbers with the same first term. The sum of the first series is r1, and the sum of the second series is r2. What is r1 plus r2? So let's take a couple minutes for everybody to work through this on their own and use the formulas and methods from above that we mentioned to try to combat this problem, because if you use the formulas from above, it makes this problem a lot simpler.
So what is with the AR2, what does that mean?
So it's just a subscript. So R subscript 1, you can almost ignore it.
At the
Like
top.
R1 and R2 are just.
I mean,
So
at the top.
R1, 2, that means R1 squared. R1 is a variable and you're squaring it.
So it's just
Yeah,
A
so A
squared.
and R1 and R2 are all variables, and you're trying to you don't need to find out necessarily what they are, but they're just variables holding the place of numbers.
Okay.
All right, so take about 1 more minute, and then I will start working through the walkthrough on the slides.
I've had a couple responses. We'll give it just another moment. You guys figure this out.
All right, I will start. We can start working on the walkthrough a little bit, and if you're still working on it, go ahead and keep working on it by yourself. So first, we start out by using the formula for the sum of a geometric sequence. So the sum of the first sequence is the first sequence, which is a plus ar1 plus ar1 squared, so on, is a divided by 1 minus r1. And the sum of the second sequence is is a over 1 minus r2. So these look really similar because the first term is different, but because their common ratio is different, that's why the denominators are different. So we are given that the sums are R1 and R2 respectively. So we can set the two equations. So A over 1 minus R1 equals R1, and A over 1 minus R2 equals R2. So for both of these equations, if we cross multiply, we get A is equal to R1 minus R1 squared, which is the same thing as R1 times, in parentheses, R1 minus R1, and that's equal to R2 times 1 minus R2. So this we're just getting by multiplying the first equation by 1 minus R1 and multiplying the second equation by 1 minus R2. And since they both are equal to A, we can set both of these equal to each other. So at this point, we can forget about A since the problem only asks R1 plus R2. We don't care what A is, just because we don't need A to solve the problem, and A was just there to kind of help us put these equations together. But now that we have an equation with R1 and an equation with R2 that are equal to each other, we can just not worry about A anymore. So we have R1 times 1 minus R1 equals R2 times 1 minus R2. And multiplying these out, we get R1 minus R1 squared equals R2 minus R2 squared. And we can rearrange these two equations a little bit to get R1 minus R2 equals R1 squared minus R2 squared. And then if you notice on the right side, R1 squared minus R2 squared is kind of the same thing as A squared minus B squared, or the difference of squares. So since it's a difference of squares, we can factorize it by saying R1 minus R2 times R1 plus R2. And if you notice now, well, both sides have a R1 minus R2, so we can divide both sides by R1 minus R2, which gives us 1 equals R1 plus R2. So our final answer is R1 plus R2 equals 1.
All right, slight technicality there, because when you have R1 minus R2, you need to be careful that that's not 0, right? Because otherwise you're dividing by 0. But in this case, we know that there are two different geometric series, so R1 and R2 are not equal, therefore R1 minus R2 is not 0. And also, another way of solving it, you could have just instead of having two different variables, R1, R2, you could have just said R, because there are two different values that are going to work. A over 1 minus R equals R. And then you can write A equals R times 1 minus R. So A equals R minus R squared, and R squared minus R plus A equals 0. Now, at this point, it's a quadratic, so you expect there to be two solutions, and you can just use Vieta's formula since you want the sum of the two. That's just negative B over A. So I think B in this case is negative 1. You're solving for R. C and A is 1, so it just becomes 1 over 1, 1. That's another way you could have done it.
Yep, so as we said, there's another way of doing it, which he just kind of verbally said right now. But yeah, both ways work, and it's just like two personal preference. So just for this problem, a quick summary. The main thing to look at is it gives you the sum of both the geometric sequences. So once you can create two equations based on the formula for the sum of a geometric sequence and the value that they give you, it's really simple then to calculate it out and to algebraically manipulate it a little bit. So we find out what R1 plus R2 is. All right. Here's our next problem. Suyash, do you want to take over here?
I'll do this one. Sorry, I keep muting myself.
All right. All right. An infinite geometric. Oh yeah, sorry.
I'll read it. So an infinite geometric series has sum 2005. A new series obtained by squaring each term of the original series has 10 times the sum of the original series. The common ratio of the original series is m over n, where m and n are relatively prime positive integers. Find m plus n. Take a moment. I think this one's a little more challenging. I'm still trying to figure it out myself, so we'll give it a little more time. Still only received one response, so we'll give it a little more time here. This is pretty challenging, but you need to figure out how to manipulate the equations in the right way. So keep at it. I've just gotten a couple more correct responses. So this is an AME problem. You'd have an average of 12 minutes to solve each problem. This is one of the earlier ones that you'd ideally like to solve a little quicker. But we'll go over the solution here right now. So let the initial term of the series be A and the common ratio be R, as always. A over 1 minus R equals 2005. That's our formula for the sum of a geometric series. Infinite geometric series, that is. Okay. Yeah, we're going to send it to me. That is the correct answer. So now we can rearrange things a little bit. You get A equals 2005 minus 2005R. Now, we also know that when we square each term, we get a new infinite geometric series that has a sum of 10 times that. So using this information, now first of all, remember when we square each term, it's a squared R squared, a squared R to the fourth. So our initial term here is actually a squared, and the common ratio is R squared. So we get this new equation that's the result. The sum is a squared over 1 minus R squared. Again, applying our formula, and that's equal to 10 times 2005. So we can actually just, since it says 10 times the original series, that's a big clue that we can do a squared over 1 minus R squared. And so now there are just some manipulations here. So a squared times 1 minus R over a times 1 minus R squared. That's just using fraction division techniques. And then the denominator factors as 1 minus R times 1 plus R. And then a squared and over a. And then the 1 minus R's cancel out because we know R isn't equal to 1. That would be illegal otherwise, so it would be equal. But R has to be less than 1. And also a squared over a. Again, a is not going to be 0. All right. We know that otherwise the sum can't be 2005. A over 1 plus R, that is equal to 10. Now we're going to combine this with the fact that we know a over 1 minus R is equal to 2005. And let's see. Okay, now we have a system of linear equations because we started with a equals 2005 minus 2005R. Now we have a equals 10 plus 10R. I'll put that in the chat. Now we got, if you keep hitting it, that's good. Now, wait, okay, never mind. So, yeah, then now this is pretty easy because either a equals 10 plus 10R equals 2005 minus 2005R. So at this point you can ignore a because it's just one equation for R. That's not too hard to solve. You get 2015 R equals 1995. So R equals 1995 over 2015. That's 399 over 403. So you just sum those, you get 802. And as a check, this is between 0 and 1, actually negative 1 and 1. And it would be kind of difficult to check that it actually works the way because that would get pretty messy. But if you're confident about the algebra here, then you won't need to do that. So does everyone understand that? I know we had a good number of people get this one. So does everyone understand this step? How? Because the sum of the new series was 10 times the original one. So we were able to use this equation here and simplify it greatly. And then eventually just get rid of a and solve for R. That's all we need. Now you could actually go back and solve for it, but that's not what we want. All right, then yeah, David,
So,
you can.
the next thing we're going to go over now is periodic sequences. So we're going to shift from arithmetic and geometric sequences to periodic sequences. And this type of sequence is often disguised, but appears in a lot of contexts. So the idea is that you're given a really wacky sequence in the form of a recursion problem. So like it would say something like a recursion problem or a recursive function just means that each term is defined by the previous term. So it could say that n equals n minus f of n equals f of n minus 1 plus 3. And then that's just defining the next term based on the previous term or something like that. So the problem will give a wacky sequence in the form of a recursion problem. And then often it'll become kind of really clean later on, but it'll seem really messy. So the best way to solve these is to write small cases. So find the first few values of the sequence by manually using the recursion, and then look for patterns. Because if the sequence repeats, then you'll know it repeats or it will be periodic. So the key is that periodic sequences repeat, and a lot of times when you find out that a sequence repeats, it's really easy to solve the problem. So these are abstract tips, and it might not be too clear right now. So let's go into a real problem and see how this works. All right. So let a of 0 be 2, a of 1 be 5, a of 2 be 8, and for every term after a of 2, so for n is greater than 2, let define a of n recursively to be the remainder when 4 times a of n minus 1 plus a of n minus 2 plus a of n minus 3 is divided by 11. Find a of 2018 times a of 2020 times a of 2022. So take a few minutes to attack this problem on your own. As mentioned, write out the first few terms of the sequence and see if you can find a pattern. You might have to list out a lot of terms, more than 10 terms even, but just take your time to kind of list out using this function that's given here, list out all the as many terms as you need to in order to kind of find some kind of pattern. And then once you found a pattern, then you should be able to solve the problem a lot easier.
So we actually did this problem in our previous class, but now we're looking at it through a different lens. So and you may have to compute several terms. So sometimes it might not be obvious right away, but in many problems like this, after a reasonable number of terms, you will notice a pattern. Give it another minute here. This is the last example we have, so no hurry. All right, we'll go over this now. Like I said, we did see this. I forget whether it was either our first or second class. So again, you have this recursion pattern. Now you just list out the first few terms. So a of 3 is 4 times 2 times 5 times 8. That's 4 times 15 equals 60. Now mod 11, that's all we care about, right? That's 5 mod 11. So a of 3 equals 5. Now you just compute the next several terms. Now by terms 10, 11, and 12, you get back to 2, 5, and 8. Question is there an algebraic way of doing this? No, I think you just have to list out several terms. I mean, there is repetition after 10 terms, but within those 10 terms, I don't see a reasonable pattern. If someone can find one, please let me know. But no, I don't think so. Now, by the time you get to 10, 11, and 12, you get back to 2, 5, and 8. And since each term is defined recursively based on the last 3, you know it's going to repeat. So it has a period of 10 because it's 10 terms, then it goes back to the beginning and repeats. So yeah, this is not, so it's not impractical. It doesn't take too long to compute each term. You just need to avoid mistakes. Which, okay, now, let's see. Each term depends on the previous 2. So now by the time you compute a of 12, you can be sure that it repeats the same 0 through 9 terms. Now, so now the key thing is that A10 equals A0, A11 equals A1, and A12 equals A2. And for example, A37 equals A7 because it repeats every 10 terms. So we want to find 2018, 2020, 2022. That's going to be equal to A8 times A0 times A2, A7, A0 equals 2, and A2 equals 8, so it's 112. So I went kind of fast here, but we did see this before. So that's all we have for today. Now, this Thursday is the AMC 10A, which I'm sure most, if not all of you, will be participating in. So yeah, so we did have our strategy session yesterday, which I'm sure many of you attended, but if you didn't, we do have a recording on our website. I think that strategy session was mainly meant for math accounts, but there are a few tips you can pick up from there that will also apply to the AMC. So be sure to check that out. Yeah, good luck to you all. And anything else, guys?
Don't think so. Thank you so much for coming.
Yep, thank you everybody for coming.
Bye.
See you guys next week.
See you all next week. Thanks.
Thank you. Bye.
Thank you.
Bye.
All right, I'm gonna end the meeting now. See you guys.